years or so in the time leading up to their discovery. In December 1933, just 2 years after the discovery of the neutron, astrophysicists Walter Baade and Fritz Zwicky proposed that supernova explosions could cause stars to turn into much denser, more closely packed bodies as a result of the explosion. A plausible theory, but at the time we were sure we'd never be able to detect such an object even if they did exist, as they would simply be too small to be observed from the Earth. But moving into the 1960s, astronomer Franco Pacini noted that if stars generated strong magnetic fields, then the electromagnetic radiation this would emit should be detectable from the Earth. And sure enough, in 1965, astronomers Anthony Hewish and Samuel Okoye discovered a source of radio brightness in the nearby Crab Nebula. This anomaly turned out to be the product of a rapidly rotating neutron star, and so we were able to conclude on the existence of these terrifying post-production stars. And then, in 1997, we did in fact see a neutron star through visible light. What you see here is an actual photograph of a neutron star of a similar mass to our Sun, which was discovered in 1992. The achievement of observing a neutron star 400 light years away in visible light is not to be understated. Whereas stars are millions of kilometers in diameter and radiate light, most neutron stars are merely about 20 kilometers in diameter, or just 12 miles. One of the largest we've discovered to date is PSR J0348, a neutron star in the constellation of Taurus, with an estimated mass of about twice that of our Sun, packed into an object just 25 kilometers wide, making it smaller than the inner ring roads of the City of London, but huge for a neutron star. Although saying that, size doesn't actually correlate to more mass within neutron stars. In fact, more massive neutron stars are actually smaller, as their mass compacts more densely than in lighter neutron stars. Regardless of how big or small they are, this size-mass ratio gives them their incredible densities, so much so that a single teaspoon of neutron star matter would weigh hundreds of millions of tons here on Earth. This incredibly compact concentration of mass means that the gravity of a neutron star is around 2 billion times greater than on the Earth. And while not as dense as black holes, this gravity is still enough to bend and warp the radiation and light being emitted around it, causing a details of a neutron star's structure by studying living stars, such as the Sun. This process is known as astroseismology, and it can reveal the inner structure of neutron stars by analysing the spectra of star oscillations. This is what gives us our insight into the real jaw-dropping numbers associated with these cocoons. The surface, or crust of the neutron star, is an extremely hard outer layer, whose surface temperature can reach up to 1 million degrees Kelvin. This crust gives the neutron star a miniature landscape. It can have mountains, but these mountains can only ever hope to reach a few millimeters high. The extreme outer layer is made mostly of iron left over from the supernova, and this iron is so compressed that it keeps the internal components sealed below the crust under unthinkable pressure. Under these conditions, atomic nuclei are crushed together in long strings of matter, trivially named nuclear pasta. Barely anything can breach this material. It is among the strongest and most tightly packed matter in the universe. As we move downwards towards the core, we start to become a bit less sure. We aren't sure what effect this much pressure this deep into the core would have on matter. However, we do know that it is able to keep atomic nuclei from decaying, allowing it to remain stable. This internal mass, density and pressure keeps it out. Well, a neutron star is formed when a massive star, between 10 times and 29 times the mass of our Sun, reaches the end of its life and explodes. At this point, heavier elements in the core begin fusing iron. Because iron has no energy to give, fusion is no longer generating outward pressure from within the star, and there is suddenly nothing to stop the star collapsing under the weight of its own gravity. The outer layers collapse inwards rapidly, with nothing to counter them, and when they reach the iron core, this matter forces the interior into a much smaller space, before essentially bouncing off the core and exploding in a violent supernova explosion. These outer layers collapse fast, at 25% the speed of light in fact. This is so fast that particularly massive stars keep on collapsing indefinitely into a singularity, creating a black hole. A neutron star is formed by the level of massive star below, star cores that are less than about 4 to 5 times the mass of the Sun. In this case, the core is not massive enough to collapse indefinitely, but what remains of the collapsed matter is minuscule in size compared to its previous form. A star once hundreds of times larger than the Sun collapses into an object the size of a city, making it among the densest objects in the universe. The reason they are called neutron stars is because the density and pressure on the interior is so great that the protons and electrons of the atoms within start to be crushed into one another, generating long chains of strong neutron-rich material under conditions similar to those of the nucleus of an atom. Neutron stars are essentially giant atomic nuclei. These dense, dead stars have extremely strong gravitational influences and magnetic fields. The chain reaction from the supernova explosion often causes the newly formed neutron star to spin incredibly quickly, with some known to rotate up to 40,000 times per minute.